How do we use differential equations in science and engineering? First, we have a real-world problem we wish to understand. We make some simplifying assumptions and create a mathematical model. That is, we translate the real-world situation into a set of differential equations. Then we apply mathematics to get some sort of a mathematical solution. There is still something left to do. We have to interpret the results. We have to figure out what the mathematical solution says about the real-world problem we started with. And here we have a diagram that shows the process. Learning how to formulate the mathematical model and how to interpret the results is what your physics and engineering classes do. In this class, we will focus mostly on the mathematical analysis. Sometimes we will work with simple real-world examples so that we have some intuition and motivation about what we are doing. Let us look at an example of this process. One of the most basic differential equations is the standard exponential growth model. Let P denote the population of some bacteria on a petri dish. We assume that there is enough food and enough space. Then the rate of growth of bacteria is proportional to the population. A large population grows quicker. Let T denote the time in seconds and P the population. Our model is dP dt equals K times P for some constant K greater than 0. Recall dP dt indicates the change in P with respect to time is equal to K times P, meaning some constant times the population P. Now suppose there are 100 bacteria at time 0 and 200 bacteria 10 seconds later. How many bacteria will there be 1 minute from time 0, meaning when the time is 60 seconds? First, we need to solve the differential equation, and we claim that a solution is given by P of t equals c times e to the power of kt, where c is some constant. Recall, if this function is a solution, then it must satisfy the differential equation dP dt equals k times p. And let's go ahead and check this by determining dP dt. To differentiate c times e to the power of kt, we need to apply the derivative formula shown below, which includes the chain rule where the inner function u is kt. And therefore u prime is equal to k, which is the derivative of kt with respect to t. So dP dt is equal to c times the derivative of e to the power of kt with respect to t, which is e to the power of kt times k, which we can write as k times e to the power of kt. So now we know dP dt is equal to c times k times e to the power of kt, which is k times p, since p is c times e to the power of kt. This verifies P of t is a solution. Okay, so now that we know P of t is a solution, what do we do? Well, we still don't know c, and we also don't know k. But we do know something. We know P of 0 is equal to 100, and we also know P of 10 equals 200. Let us plug these conditions in and see what happens. Given P of 0 equals 100, we can write the equation 100 equals P of 0, and P of 0 is equal to c times e to the power of k times 0, or just e to the 0, and e to the 0 is equal to 1, giving us c is equal to 100. So now we know P of t is equal to 100 times e to the power of kt. And now using P of 10 equals 200, we can form the equation 200 equals P of 10, and P of 10 is equal to c, which we know is 100, times e to the power of k times t, but t is equal to 10, giving us e to the power of k times 10. And now we solve this equation for k. To solve this equation for k, the first step is to divide both sides by 100, which gives us the equation 2 equals e to the power of 10k. And I've shown some extra work to solve for k above here in the blue box. The next step is to take the natural log of both sides of the equation. Notice on the right we have natural log of e to the power of 10k. Applying the power property of logarithms, natural log of e to the power of 10k is equal to 10k times natural log e. Natural log e is equal to 1, giving us the equation natural log 2 equals 10k. Dividing both sides by 10, we now know k is equal to natural log 2 divided by 10, or as a decimal, k is approximately 0.069. So now we know that P of t is equal to 100 times e raised to the power of kt, which gives us the product of natural log 2 and t divided by 10 as the exponent. Or if we use a decimal approximation for natural log 2 divided by 10, we have P of t is approximately 100 times e to the power of 0.069t. And now we can determine how many bacteria after 1 minute or 60 seconds by determining P of 60. And I've shown the work in the calculator below. Notice if we use the exact value of k, we get exactly 6,400. If we use a decimal approximation for k, we have much more of an error. We'll go ahead and say at 1 minute or t equals 60 seconds, the population is p of 60, which is 6,400 bacteria. On the right, we have the graph of p of t, which shows the population increasing as the time increases. Let us talk about the interpretation of the results. Does our solution mean that there must be exactly 6,400 bacteria on the plate at 60 seconds? The answer is no. We made assumptions that might not be true exactly, just approximately. If our assumptions are reasonable, then there will be approximately 6,400 bacteria. Also, in real life, p is a discrete quantity, not a real number. However, our model has no problem saying that, for example, at 61 seconds, p of 61 is approximately 6,859.35. Normally, the k in p prime or dp dt equals k times p is known, and we want to solve the equation for different initial conditions. What does that mean? Take k equals 1 for simplicity. Suppose we want to solve the differential equation dp dt equals k times p, where k is equal to 1, giving us the equation dp dt equals p, subject to p of 0 equals 1,000. Then the solution turns out to be p of t equals 1,000 times e to the power of t. And I've shown some extra work here on the right. If we're given that k is equal to 1, we know p of t is equal to c times e to the power of t. Using the initial condition, p of 0 equals 1,000, we have the equation 1,000 equals c times e to the 0, which indicates c is equal to 1,000. We call p of t equals c times e to the power of t the general solution, as every solution of the equation can be written in this form for some constant c. We need an initial condition to find out what c is in order to find the particular solution we are looking for. In this case, the particular solution is p of t equals 1,000 times e to the power of t. Generally, when we say particular solution, we just mean some solution. I hope you found this helpful.